Now we shall start with new chapter, electrostatic potential and capacitors. During this journey you have to follow my concepts, what I am teaching you. Okay, now let us start with potential. Means you could have heard among your friends that you have a potential, you have a capacity to do something. Every man, every living thing in the universe has their own potential, have their own capacity to store some knowledge. They have some stored knowledge and they have some caliber like that. Suppose if I have an empty vessel, you just go on adding the water. What happens now? Level of water increases, height of water increases. So you will say pressure increases. Like that, if I had heat, if I supply heat to a body, to a good conductor of heat, when it absorbs heat, you will say there is increase in temperature. On adding water, level of water increases, pressure increases. On giving heat to a body, a good conductor of heat, its temperature increases. If you say, if I remove water, level decreases, pressure decreases. If I extract heat, temperature of the body goes on decreasing. Like that. For a body, if I add a charge, on giving charge to a conductor or to a body, you must say level of potential increases. Suppose if I remove a charge, you must say level of potential decreases. Means if I have two objects here, A and B, if A has more charge than that of Q2, I have two objects or two bodies where a body A has more charge than B. You must say that level of potential A is greater than that of potential of B. A body having greater charge has greater potential, greater electric potential. Means it can acquire more charges. More the charges, more the level of potential. Lesser the quantity of charge, lesser the potential. Therefore, you must have some relation between the electric charge and the potential. So conclusion is, a body when it is charged, its electric potential increases. Now we have to calculate the electric potential at a given point. Say I have some source charge here. Source means it is producing its own electric field. It has its own electric field in certain region. Means if I take this as a charge as positive, so you will have the field lines which are radially outward. For a positive charge, electric field lines are away from the charge. In this electric field, in the presence of electric field, I must calculate what is the potential at the point of consideration, say at a distance r from the point charge. Question is, in the uniform electric field, you have to determine what is the electric potential at the point of consideration at a distance r from a source given charge q. For determining this, you must be able to define what do you mean by electric potential. To define electric potential at a point, I must have some reference point. So at infinity, I must have some reference point. To determine potential at a given point, I must choose some reference point where potential is 0 and electric intensity is 0. Here, for example, you want to measure a length of a board or length of your hall. You will take a scale, meter scale. What is the reference? 0 mark. If it is a 10 meter, you will say it is 10 meter. That is, you have measured the length of the hall from using a meter scale whose reference point is 0. Temperature of the room, you will say 30 degrees Celsius. What is the reference point? 0. Like that, to determine a potential at a point, I must have some reference point. We choose reference point as infinity. Don't go to infinite, means usually we take that as earth. The earth itself is chosen as an infinite point where the electric potential and electric field is 0. Usually for earth the potential is very slow but negative, very low. This value is almost taken is equal to 0. So we take the earth as a reference where the potential is 0 and electric intensity is 0. Now to define a potential at a point, I have to bring some test charge, that is unit positive charge, plus 1 coulomb charge is taken as a reference charge, test charge. Now this charge has to be brought from a point where the potential is 0, means from infinity, to the point of consideration. To carry a charge, you need some work, and that work done per unit charge is always known as potential at a point. Work done per unit charge in bringing it from infinity to the point against the direction of electric field. You are doing some external work. When you do some external work, and that work done will be stored as potential energy. But before learning that, the amount of work done per unit charge, you must say per unit charge, in carrying it from infinity to the point under consideration against the electric field is known as electric potential. Now this can be written in mathematical form, that potential at a point is work done in carrying unit positive charge from infinity to the point under consideration against the direction of electric field. Now by this definition, can you recall what is the SI unit of work done? That is expressed in terms of joule. Charge is expressed in terms of coulomb. Joule per coulomb is a SI unit of electric potential, or the same can be written in terms of volt. SI unit of electric potential is joule per coulomb or volt. Since potential is measured as a work done, this electric potential is a scalar. And don't worry about the direction as we done in electric intensity. Potential is amount of work done per unit charge in bringing it from infinity to the point of consideration against the direction of electric field. It is a scalar quantity has only magnitude, no direction, and SI unit is volt. Now let us define 1 volt. Now from this formula, this potential is 1 volt. Potential is 1 volt. To transfer whom 1 coulomb of charge, you need work. You need energy. You have to spend some energy. How much energy you have to spend? 1 joule of work. Therefore, if I say potential at a point is 1 volt, 1 joule of work is required to transfer 1 coulomb of charge from infinity to the point against the direction of electric field. Suppose if somebody asks, define what is 5 volt? Potential at a point is 5 volt. Means what? You need how much joules of energy? 5 joules of energy is needed. Why? To transfer a charge of 1 coulomb from infinity to the point against the direction of electric. So I think you understood the basic. Now, question is, after learning this basic definition, you have to derive or deduce the relation. For a board paper, you may expect this for a 5-mark question. Question is, you have to prove the relation. What is this V? Potential at a point. In an electric field, at a point, in an electric field, due to a point charge, let us take this point charge as say Q. It may be capital Q also. I have written small q here, so I write small q. Listen, my dear students. To prove this formula, you must have a basic definition of this. And who is producing this electric field? This electric field is produced because of source charge. This is given charge. Where it is kept, they may give in vacuum, or they may say free space. As you know, epsilon naught is permittivity of free space or permittivity of air or vacuum. Its value is 8.854 10 to the power of minus 12 coulomb square per Newton per meter square. The value of 1 by 4 pi epsilon naught is 9 into 10 to the power of 9. You already practiced this value. 1 by 4 pi epsilon naught is 9 into 10 to the power of 9. While doing problems, let us apply this. Before doing problems, let us say how this formula can be derived. To start with the derivation, let Q be the point source placed in free space. P be a point at a distance r from a point charge. To determine electric intensity at a point P, we have to start our journey from infinity. Means we have to take one variable, say x is the variable, which is going to start from, it is going to start its journey from x equal to infinity, and this variable is going to stop at this point where x become equal to r. For calculating potential at point P, we have to carry a test charge whose value is 1 coulomb of charge from infinity. This is taken as reference point where potential is 0, electric intensity is 0. To measure potential at a point in an electric field, we must choose some reference point. What is the reference point? Infinity. It is said to be potential is 0 and electric intensity is 0. From that point, you are bringing this charge. Now we have to do some total work. We cannot do the total work at the same time. We take a small amount of work done. Let us say this charge is being carried now. 1 coulomb of charge is carried now from infinity. So let us say at a certain time, after certain time, our charge has taken some position here, some position. Test charge has reached some point near to it. During this entire journey, we have to carry this charge in a small speed. You should not have some acceleration, not accelerated, no acceleration. It has to be carried very slowly, very slowly. So let us say at some time, the charge is at, say, A. At A. Now this, if I say this arrow mark, what do you feel? The charge is carried against the direction of electric field. Let us say through a small distance dx. And the charge is traveled a small distance, say from A to B. Charge has traveled a small distance dx, that is from A to B. Therefore, small amount of work done in transferring unit charge. Work done per unit charge. In transferring it. In transferring it. From where? From where? Infinity, that is x equal to infinity, to x equal to point of consideration is R. This is the definition of electric potential at a point T. Work done per unit charge. In transferring it from infinity to the point under consideration against the direction of electric field is the potential at point, given point in an electric field. Now, we are doing some mathematical calculations. You have learned some physics steps here, my dear students. Now some mathematical calculations. From this, work done is what? I write dot product of two vectors. I think you are familiar with this now. Divided by Q naught. Just take the variable that is from infinity to R. Integrate with respect to x. Means variable x is varied from x equal to infinity to x equal to R. No need to write x equal to. It is understood. X is the variable. You are integrating from infinity to R means x is varied from infinity to R. Now this term becomes how much here? By the definition, this becomes what? Potential now. Now listen here. F dot dx, dot product of two vectors. Now this electric field is what? The force acting on a test charge. Force on a test charge gives the electric intensity. Now I just expand this now by your dot product formula, that is F into dx into cos 180 divided by F. F is F by Q naught. F by Q naught is E into dx. Here E and dx. I repeat the same. No need to take too many steps over here. F dx cos theta. F by Q naught. F by Q naught is what? E. So E into dx into cos 180. Why cos 180? Here electric field direction and the displacement. Charge is carried against the direction of electric field. Therefore, we have displacement is 180 degree. Displacement and electric field direction are 180. Here, do not write the vector symbol. They are magnitudes. So now, what is the variable here? X. From infinity to R. What is cos 180? Minus 1. What is the electric intensity at a point? At a point, say somewhere where it is here. Now this is being carried now. I just rearrange this. At any point, say now it is carried. Now I told earlier, x is varied from infinity. It is being traveled now. Now x is varied. At this point, now x value has reduced to some value, not infinity now. So therefore, electric intensity formula is 1 divided by 4 pi epsilon naught q divided by x square, x negative sign. I take it outside. Electric intensity is 1 by 4 pi epsilon naught q by x square. X is the variable. Don't put infinity. If you put infinity, it becomes 0. Now it is being carried now. Permanently the charged particle is not at infinity. It is being travelled at some point of consideration, not p. At somewhere, the x is some value. It has some value. Therefore, don't put here x equal to infinity. So now, from this, 1 by 4 pi epsilon naught and q is constant. Take it outside. Minus q divided by 4 pi epsilon naught. What is left here? Integration of 1 by x square with respect to x from infinity to r. 1 by x square integration is minus 1 by x. Integration of 1 by x square is minus 1 by x. Minus of minus plus. Q divided by 4 pi epsilon naught 1 by x from infinity to r. You have integrated this. Minus of minus become plus. I have written the value here. 1 by x square integration is minus 1 by x. Minus of minus plus. Upper limit is r. Lower limit is infinity. Q divided by 4 pi epsilon naught 1 by r minus 1 by infinity. 1 by any number by infinity is 0. Therefore, final answer is 1 by 4 pi epsilon naught q divided by r is the expression for electric potential at a point in an electric field produced by a point source, point charge q, which is taken as a source. ನೋಡಪ್ಪ ಏನು ಸಮರಿ ಏನಂತಂದ್ರೆ ಕ್ಯೂ ಚಾರ್ಜ್ ಕೊಟ್ಟಿದ್ದಾರೆ, ಅದರ ಸುತ್ತ ಏನಿದೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಇದೆ. ಇಫ್ ಚಾರ್ಜ್ ಮ್ಯಾಗ್ನಿಟ್ಯೂಡ್ ಜಾಸ್ತಿ ಮಾಡೋ ಇಂಟೆನ್ಸಿಟಿ ಆಫ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ, ಪೊಟೆನ್ಷಿಯಲ್ ಕೂಡ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. ಚಾರ್ಜ್, ಪೊಟೆನ್ಷಿಯಲ್, ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ದೇ ಆರ್ ರಿಲೇಟೆಡ್. ಒಂದು ಬಿಟ್ಟು ಇನ್ನೊಂದಿಲ್ಲ. ಇಫ್ ಕ್ಯೂ ಇನ್ಕ್ರೀಸಸ್, electric intensity also increases, the potential also increases. But last, how this potential and are related? Inversely proportional. Potential at a point is inversely proportional to the distance. And since potential is a scalar, don't worry about the directions here. As we studied in electric intensity, if I have a positive charge, field lines are away from the charge. If I have a negative charge, field lines are inward towards the charge. When you are calculating electric intensity, you think of direction. Whereas when you are considered potential, don't think of the direction, but you must think of, okay, I think you understood this. I feel you have taken this. Now last discussion of this is, so from this positive charge, field lines are away from the charge. We have done some mathematical calculation, we got positive. Therefore, potential at a point due to positive charge, that is Q, greater than 0. Potential at a point due to a positive charge means Q greater than 0. Potential is positive. 1 divided by 4 pi epsilon naught q divided by r. Suppose if the given charge is negative, I think you have taken this. So when q greater than 0, potential is positive. So if I have a negative charge, in the derivation, we have done this, that is f dot dx. I have negative charge here. Source charge is negative. Field lines are inward. Now the test charge, that is plus 1 coulomb of charge. Now if you answer, the force, that is electric field, is electric intensity is force by charge. Direction of electric field and the displacement are in the same direction. If we expand this, we have written this: work done per unit charge from infinity to the point under consideration, that is equal to infinity to r f dx cos divided by q naught. Here what is theta now? 0. Because electric field and the displacement means a charge particle is carried along the direction of field. Theta becomes 0, cos 0 is 1, f by q naught is E. So as we studied, q divided by 4 pi epsilon naught, I just write this step dx from infinity to r. Now what is 1 by x per integration? Minus 1 by x. So q divided by 4 pi epsilon naught minus 1 by x from infinity to r. What is the upper limit here? R. That is minus q divided by 4 pi epsilon naught. Any number of upper limit minus lower limit. Just I am showing you that if I have a negative charge as a point charge, source charge, you must take the potential due to negative charge. Since potential is a scalar quantity which is measured as work done per unit charge, you should take off plus potential when given charge, point charge is positive. When the given charge is a negative, point charge, source charge is negative, potential is negative. While doing problems, don't bother about the direction, just think of the sign. Now, there is one important relation between electric intensity and the potential. Means to prove E is equal to minus dV by dr. Obtain the relation between electric intensity and the potential. Here, this formula itself, we say that any physical quantity that is measured with respect to some distance, any physical quantity measured with respect to some distance, we call that as gradient. Any physical quantity measured with respect to distance is known as gradient. Here what is the quantity now? Potential. Potential gradient. Here with negative sign, you must say negative potential gradient. And this negative sign also shows that whenever you go along the direction of electric field, so let us say electric field direction is right side. Because of positive charge, say if I take q greater than 0, field lines are away from the charge. If I choose some points here, say V1 and V2, from the point charge q, how far it is? R1. Here to here, let us say this distance is R2 now. Now as we studied how potential and distance are related here, potential is inversely proportional to R. Here from this, if I say R2 is greater than R1, since V is inversely proportional to R, can you tell among V1 and V2 which point has greater potential? That is V1. As distance increases, potential decreases. Means V2 is lesser, V1 is greater. So from this you can say V2 is less than V1. That means if you carry a charged particle, say from point 1 to point 2, means along the direction of electric field, what happens? Potential decreases. That is the meaning of this negative sign. Negative sign in the formula tells you that along the direction of electric field, electric potential decreases. With this discussion. Okay, now you understood what this negative sign tells you. To prove this formula, you take a uniform electric field. This exists only for a small region. In this uniform electric field, let us choose that there are 2 points A and B. Has some potential VA and VB, and of course VA is greater than VB. Now take a test charge, that is Q0. Unit positive charge has to be carried from lower potential to higher potential through a small distance, let us say dr. You can choose dx also, x. Here I have taken dr. You can take your own letters. Usually dx or dr. Say unit positive charge is carried from lower potential to higher potential, means against the direction of electric field. Here again electric intensity is the force exerting on a test charge, a force acting on unit positive charge. So when it is carried against the direction of electric field, you must do some work. So that work done, small work done, in carrying a charge from where to where? Not infinity here. From B to A. B to E. Small work done per unit charge. From one point to another point against the electric field is always known as potential difference. The difference in potential. Here there is a difference in potential. VA is greater than VB means what is the difference in potential? VA minus VB. Suppose if it is 10 volt, if it is say 5 volt, what is the difference now? 5. You cannot write 5 or 10. No, wrong. VA should be at higher potential, say 100 volt. Let us say B is at 70 volt. 100 minus 70 is 30. So that is the potential difference. Amount of work done per unit charge. I repeat, this word is very important. Work done per charge gives potential. And the total work done is stored as potential energy. Potential energy solve ಮಾಡಬೇಕಾಗುತ್ತೆ. So calculate the potential energy and it is work done. We shall see in the next coming classes. For defining potential, you must say work done per unit charge in bringing it from one point to another point is known as a potential difference. Now as we done, this work done is what? Force into displacement. Here it is R, F dot dr, dot product of two vectors divided by Q naught. Just expand this, F dr cos, can you tell this? 180. Why 180? Field direction and the displacement are opposite. Suppose if it is there in the same direction, take as positive. 0, 0. Now it is 180. Electric intensity and the displacement of the charge are opposite in direction. Theta is 180 divided by Q naught. What this F by Q naught gives? F by Q naught gives electric intensity Therefore, dV is equal to, I write, minus E into dr. Therefore, this electric intensity is minus dV by dr. I think you understood. Easy. For 3 mark, you will obtain the relation between electric intensity and potential. Here I have written vector. It is vector. Don't write here. Potential is a scalar. Now can you tell me the SI unit now? Potential is expressed in terms of volts and distance is expressed in terms of meter. So SI unit of electric intensity, practically now onwards you can use volt per meter. Now can you again recall what I said? Any physical quantity measured with respect to distance is known as gradient. What is the numerator? Potential. Potential gradient. What is the negative sign here? Of course, negative sign, what you will say? Sir, displacement and the electric intensity are opposite. Force and electric intensity, that is electric intensity and displacement are opposite. Electric intensity and the displacement are opposite. Both are opposite. You will say cos 180. How much you will get? Minus 1. Fine. It is good. But the exact meaning of this negative sign is that if a charged particle move along the direction of electric field, you must say there is decrease in potential. Again, I give you one note which is essential for your competitive papers. From this, dV is equal to minus E into dr. From this, I rearrange one formula here. You must memorize. That formula is essential for your competitive papers. Potential is scalar. Electric intensity is vector. Displacement is vector. Therefore, potential difference can be written as dot product of two vectors. Now let us understand one simple problem over here. So they have given potential as a function of x here. They are asking what will be the electric force on minus 2 nanocoulomb placed at a distance x equal to 2 centimeter. Can you pause and answer? So here force is what? E into Q. Force is E into Q. Now, they have given potential. As we studied, E is minus negative potential gradient means dV by dr. You must say now differentiation of potential with respect to distance. Differentiation of potential with respect to displacement. Now here x is displacement, v is potential. Differentiate with respect to x. So dV by dx. Now, my dear student, x is the distance now. So that is equal to 4x square is 8x plus 2. Differentiation of constant is 0. So now at x equal how much they are asked? 2 centimeter. 8 into 2, 10 to the power of minus 2. 16 into 10 to the power of minus 2 volt per meter. What they have asked? Now you got this electric intensity now. Now I got E is equal to minus dV by dx. That is equal to, how much you can write? Minus 16 into 10 to the power of minus 2 volts per meter. Now what they asked? They are asking the force. Therefore, F is equal to, can you answer? The electric field is minus 16, 10 to the power of minus 2 volt per meter. What is the charge they are given? Minus 2. Nano means 10 to the power of minus 9. So can you answer? Minus of minus plus. This is how this formula is helpful in finding electric intensity. Now you will have plenty of problems. That problem session will be different. Just understand how this formula is useful in your coming classes. Now let us understand one problem that will appear in your papers. 5-mark problem based on this. Now for that I have something called principle of for doing problem. This concept is very essential. Principle of superposition means you have to add some potentials. Remember, potential is a scalar. Now let us say P is a point. I have so many charges here. N system of charges, may be positive, may be negative. So Q1 is at a distance RP1. RP1 means distance between point and the first charge. Say this is RP2, RP3 and so on. RPN. Simple concept. Question is, what is the total potential at point P due to system of these point charges? Basic thing is, just imagine that P is surrounded by how many charges? P is surrounded by how many charges here? N charges. Now what this principle of superposition tells you that total potential at the point of consideration, is the scalar sum of all the potentials taking one charge at a time. Means V1, potential at point P due to charge Q1, taking charge, one charge at a time, means V1, potential at point P due to Q1, V2, potential at point P due to charge Q2, so on, Vn, potential at point P due to charge N. Now just do the scalar addition, don't bother about the directions because problems are easy. Many students they feel that problems are very tough. No, problems are very easier. Yage concept ಚೆನ್ನಾಗಿ ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕು. ಏನಪ್ಪ ಕಾನ್ಸೆಪ್ಟ್? ಒಂದು ಸಿಸ್ಟಮ್ ಆಫ್ ಚಾರ್ಜಸ್ ಕೊಟ್ಟಿದ್ದಾರೆ. ಪಾಯಿಂಟ್ ಪಿ ಹತ್ರ ಪೊಟೆನ್ಷಿಯಲ್ ಕಂಡುಹಿಡಿ, ಸ್ಕೇಲರ್ ಅಡಿಷನ್ ಮಾಡು. Now let us have one problem on this. Now the question is this. 3 point charges are given, placed at 3 corners A, B, C of a square of side 1 centimeter. Say 2 microcoulomb minus 1 microcoulomb, say plus 3 microcoulomb. Given point charges at the corners A, B, C respectively of a square of side 1 centimeter. They are asking work done. In transferring say 2 microcoulomb from corner D to the point of intersection of the diagonals. Work done in transferring a charge of 2 microcoulomb from corner D to the point of intersection. This is the point of intersection. Means you have to calculate work to transfer this much of charge from D to O. Charge move from one point to another point because of potential difference. And then work done in carrying the given charge. Work done per charge in carrying it from one point to another, is always known as potential difference. not the potential. Potential difference. Work done in transferring, work done per charge. In transferring it from one point to another point. They are asking work done. Therefore, work done is equal to what? Potential difference into the charge that is being carried. This is the concept that you must have in the knowledge when you see a problem. Now, potential difference and potential difference in the potential. It is carried from where to where? D to O. Now you have to write the final VO minus VD into Q. Charge move from one point to another point because of difference in potential. Suppose if it is at 5 volt, this is also 5 volt. What is the difference in potential? 0. Can you say charge move? No. First point to remember. Charge move from one point to another because of the potential difference. Potential difference definition you have already taken. Then point to be noted is D2O. What is the final point here? VO minus VD. I will confuse everybody. Potential difference in potential. Final minus initial. Difference in temperature. Final temperature minus initial. Displacement. Final position minus initial. Difference in potential. Final potential minus initial. What this VO represents? O is a point of intersection. This point O is surrounded by how many charges? 1, 2, 3. And one my suggestion. The charge that is being transferred, don't put that charge at that point D at the beginning. Don't put the charge which is being carried. That charge has to be multiplied over here. Okay, don't put the charge that is being carried. Now O is surrounded by 3 charges A, B, C. By the principle of superposition, potential at point O is this. Scalar addition. It is the sum of potential at a point due to individual charges. And as you know, V is equal to 1 by 4 pi epsilon naught Q divided by R. For doing problems, 1 by 4 pi epsilon naught is 9 into 10 to the power of 9 into Q by R. R is what? Distance between the charge and the point of consideration, means here to here. OA, OB, OC, OD, they are all semi-diagonals. OA is equal to OB is equal to OC is equal to OD. Now from the geometry, you can write the diagonal. AC is equal to DB, that is equal to root of whatever they give. Here how much they are given? Centimeter. Make it as centimeter. 1 square, 1 square. How much? 1 square, 1 square. 1 plus 1, 2. 1 plus 1, 2. So that is root 2 centimeter. This distance is root 2. Semi-diagonals means root 2 by 2. Semi-diagonal OA, OB, OC, OD, they are all equal to half of the diagonal root 2 by 2. So how much you will get? 1 by root 2 centimeter. These are all semi-diagonals. After calculating these things, now from these, what is the common term that you can take out? 9 into 10 to the power of 9. And all distances are same here. That distance is how much? R. Distance is R here. This R is a constant here. Take it outside. For this, you are writing the formula. I am taking the common terms here. What is the R here? 1 by root 2. 1 by root 2 centimeter. Centi means 10 power minus 2. What is left now? I have taken 9 into 10 raised to 9 divided by R. And one more. In charge, micro is there. So 10 to the power of minus 6. What is left now? Only the magnitude, that is 2 plus 2. Potential is a scalar. Therefore, I told If it is a positive charge, take positive. Second, minus. Then potential at O due to charge, how much it is? Plus 3. 2 minus 1, 1. 1 plus 3, 4. 4. 4 nines are 36 into 10 to the power of 9 minus 6, 3 plus 2. 9 minus 6 plus 3. Minus 2 ಮೇಲೆ ಕಳಿಸಪ್ಪ ಎಷ್ಟಾಯ್ತು plus 2. So 10 to the power of plus 5. One more, 1 by root 2, take it numerator. So your answer, potential at O is 36 root 2, 10 to the power of 5 volts. SI meter potential is volts. Take a calculator and then solve this. Okay? Now, work done is what? Potential difference into charge. Now, you got potential at O. Now, potential at D. D is surrounded by how many charges? 3 charges. What are they? Charge at A, B and C. As you done in the potential at O, can you solve potential at D? Same steps. I repeat the same and I jumped some certain steps over here. What is the first term? 1 by 4 pi epsilon Q by R. For each potential, you have some formula. 9 into 10 to the power of 9 is common. Charge. In the charge, microcoulomb is common. Difference is the distance here. This distance is 1. This distance is root 2. And this distance is 1 centimeter. This is root 2. Understood? Now, okay, let me write one step for you. 1 divided by 4 pi epsilon naught. Charge at A divided by the distance dA, D to A, plus charge at B divided by distance dB, plus one more charge is there. What is that? Charge at C. Charge at C divided by the distance is dc. So what done is potential difference into charge. We have calculated potential at O now. We have to solve for potential at point D. Potential at D. D is surrounded by how many charges? 3 charges. Potential at a point is given by 1 by 4 pi epsilon Q by R. 1 by 4 pi epsilon naught is 9 into 10 power 9. So I have done, if you feel fast, I am slow here, you can understand better. Potential at D is 1 by 4 pi epsilon naught Q by dA plus, this is taken as common, charge at B divided by distance dB plus charge at C divided by dC. I told in the beginning, not all the students, few students who do not follow our step, they do mistake. The charge being carried, do not place at this point. What is the value of this? 9 into 10 to the power of 9 into. What is the common term you can take as we done in the previous? 10 power minus 6. Yakapa? Micro. Here distance was common. Here distance you cannot take as common, but you can take 10 power minus 2 as common. Centi. So what is left now? Charge at A, 2 plus 2. Potential due to negative charge is negative, minus 1. Same. Due to charge at C, that is plus 3. Here, dA is how much? 1. I have forgotten this. 2 by 1. Centi is taken outside. Minus 1 divided by, what is the total distance here? Root 2. All divided by dc is how much? 1 centimeter by 1. So I have taken centimeter common now. Just apply your mathematics. Potential at D. I just remove that. Further simplification. 2 plus 3 how much? 5. minus 1 by root 2. 5 minus 1 by root 2. What is left here? 9 into 9 minus 6 plus 3. Take to the numerator 9 into 10 to the power of 5. This is potential at D. Potential at D is, now you take again LCM here, 9 by root 2 into 10 to the power of 5, root 2 LCM. Root 2 LCM. So how much you get? 5 root 2 minus 1. You simplify this. Take your calculator, simplify. Then you have to solve for potential, the work done. That is equal to potential difference into charge. It is your work. I don't want to waste the time here taking calculator and calculation. Do the calculation. Potential difference is what? Charge is carried from D to O. Final point is O. VO minus VD. VO minus VD into the charge that is being carried. Now you have to do your own. V0 minus VD you have to solve. What is the charge that is being carried? 2 microcoulomb. 2 into 10 to the power of minus 6. And that work done is, get some value. We express that in terms of joules.